video is about fuel cells. You need to know about fuel cells. You need to know about hydrogen fuel cells and methanol fuel cells. There are many good videos and textbook sections on these. This is meant to be a little summary, reminder, and a refresh. I'll have a look at a couple of exam style questions as well. So before we look at this kind of very simple diagram of an alkaline fuel cell, I'm just going to remind you that a fuel cell, the whole point of hydrogen fuel cell, and the same logic applies to methanol fuel cells, is that the fuel, in this case hydrogen, reacts with oxygen to form water. So essentially this is a combustion reaction, isn't it? If you take hydrogen and burn it with oxygen, you get a nice big bang. It's an exothermic reaction, you generate water. In a fuel cell, you generate, instead of a big bang and lots of heat and light and sound and all that kind of energy that's released, we can convert this to electrical energy. All right, so hydrogen is combined in a fuel cell with oxygen, electrical energy is generated. So it's an overall very simple reaction. Before we look at the chemistry of that in a little bit of detail, think about what the advantages of that are. So if we're using a hydrogen fuel cell to generate electricity, the couple of really key things are that water is the only product. There's no carbon dioxide as a byproduct, and of course carbon dioxide associated with climate change and so on. And there's also a direct conversion of chemical energy into electrical energy, which is more efficient than burning hydrogen and maybe using that heat to generate electricity. The major con, though, or the negative side of it, is the supply of hydrogen. There's no sort of efficient way to produce huge amounts of hydrogen in a green way at the moment, and most hydrogen that's produced requires fossil fuels currently. So, for example, it's a process called reforming of methane, which generates H2. So you really ought to be able to talk through what's going on here. So this is the negative electrode and the positive electrode. We'll name those in a moment. The hydrogen at the surface of the negative electrode is converted to water, and clearly that's an oxidation process. And so if it's oxidation, is the anode. Conveniently, the word anode has got an O right in the middle of it, which can remind us that at the anode always oxidation takes place. So that's the anode over there, and the positive electrode therefore must be the cathode, where in fuel cells that's where reduction takes place. Okay. So if hydrogen is converted to water, we need to be able to work out the half equation for that. Now, we're well practiced at working out half equations when there is H plus present, when there's acid present. We need to work it out in this case when there's OH minus present, because this is an alkaline fuel cell. So it's easy enough to work out, because here hydrogen is being oxidized. Each hydrogen, which is oxidation state 0, is converted to oxidation state +1, and so that's going to require the loss of 1 electron per hydrogen and its oxidation, and so 2 electrons are required for that process. And we know it's hydroxide that's required for this reaction, because it's an alkaline fuel cell. We'll talk about what goes on there in a sec. So to balance that equation, you can see what's happening is the hydrogen combines with 2 hydroxide ions to give water and 2 electrons. Now those electrons travel from the negative electrode, are kind of, if you like, pushed by the negative electrode round the circuit here to the positive electrode, and if you've got a component up there, they're like a bulb, you can see it light up, or an engine, a motor, something like that. And we can think about what happens at the positive electrode too. There's nice ways of working out the reaction here, or the half equation here, but it's worth remembering that we have to produce hydroxide, and the only other thing around is water. So this is not a conventional way to think about it. I'm going to show you a snapshot of a book that shows you a different way of thinking about it, but I like this way of thinking about it. So I remember the oxygen's got an oxidation state, 0 oxidation state oxygen. Here is 2 minus, and it's going from 0 to 2 minus twice. So that's going to be a 4 electron change. Put my 4 electrons on the left hand side. And the only way to make this balance is if there's 4 hydroxides produced, and it's balanced if you put 2 waters there. Now there's another way of showing that, working that through, but that's the reaction that's going on at the cathode, the way that I remember it. Have a look at this book, pause this and have a read if you want to think about a different way of approaching this. The key thing is to know you can work out those reactions, those half equations. When you combine those half equations and cancel everything out, you end up with that. So what happens to the hydroxide? Well, the hydroxide passes through this region here. So it's an electrolyte. The hydroxide passes through a membrane. We don't need to think about that or know anything about that really. All we need to know is that the reactions, these two half equations, are separated from each other. Oxidation over here, reduction over here, transfer of electrons around there, and the hydroxide electrolyte passing through here, and that's where the water is produced. Yeah, well, I guess there's not much more to add apart from that the hydroxide is produced here. Okay. You can also have methanol fuel cells. You know what, we didn't spend all that long on this in class, and I think we should certainly revise this. But again, this is just a combination of methanol with oxygen. The overall reaction is probably the most important thing you can get your head around. I'm going to give you the balanced equation, though you'll be able to balance it yourselves under pressure, as long as you remember that methanol combines with oxygen in this thing to generate carbon dioxide and water. We're going to start with the kind of pros and cons of this. So one of the big pros is using methanol as an alternative fuel to hydrogen is that methanol is a much more stable liquid at normal environmental conditions. It has a high energy density and it's easy to transport. I'll make a note of those things. So I'd say these 2 points here that I've made about the high energy density, I've seen that quite a lot in books and notes that I've picked up on here when preparing for this. So really the high energy density of the methanol is a key thing. This reaction generates more energy than the hydrogen fuel cell. You need to know the numbers, but it generates more energy. Also, if you compare methanol with hydrogen you've got to put the hydrogen in a really highly pressurized form in a big canister, and so methanol's much better in that sense. Again, methanol is oxidized at the anode, and just like before, the oxygen supplied at the cathode is reduced. But this is usually done under acidic conditions, so we need to think slightly differently about the equations. So the overall reaction there I've given to you. The two half equations are as follows. So the methanol reacts to form carbon dioxide, 6H plus, 6 electrons, and H2O liquid there. Now if you think about that half equation, that's just the way that you were taught to balance half equations. Just put the state symbols in. So it's methanol going to carbon dioxide, balance the hydrogens with H plus, balance the oxygens with water. But the other way around, of course, start with the oxygens, then the hydrogens, and then balance the electrons last of all. That's how we've approached it. There's different ways of doing it, but that way works. And the half equation at the other side is oxygen turning into water. We balance that in exactly the same way. So the 2 oxygens, 4H plus and 4E, and when you combine those two half equations, you've got to recognise that there's 4 electrons on the left, the reduction process, and 6 on the right in the oxidation process. So when you combine them, you end up with that 2 to 3 ratio that you see up there. I'm not going to write it all out again. The disadvantages of using a methanol fuel cell as opposed to a hydrogen fuel cell are around the potential toxicity and the hazards of methanol. So methanol is also highly flammable, but methanol, you might know, is toxic. If you were to consume methanol, it can cause problems with eyesight, and I can't remember if it's liver or kidney. I think it's liver that's damaged. Anyway, it's toxic. That's what you need to know. So here are a few questions I got the computer to spit out. What are the half reactions at the anode and cathode? Take your pick. The answer, hopefully you agree, is D. Exactly what I've just taught you. What's the situation with A? A is given as the right answer by the computer. Why has it done that? Well, let's just go through them all quickly. So C can't be right. It's got all the reactants back to front. It's got the fuel and the oxygen on the wrong side, so it simply ain't C. It ain't B because yes, the hydrogen's converted to H+, and the O2 is converted to H2O, which is one way of looking at this, and I'll cover that in a second in a bit more detail. But this is oxidation, and this is reduction, so it ain't that. These are perfectly reasonable half equations if you're looking at an acidic fuel cell, hydrogen fuel cell. But much more commonly, we've got an alkaline fuel cell, which is why D is the correct answer. They're both possible. What is a key advantage of methanol? You've seen it now anyway. What's the key advantage of methanol compared to a hydrogen fuel cell? So the higher energy density we just talked about. State the half equations for what's going on in an alkaline hydrogen fuel cell, and that we've just done. Why are fuel cells considered more efficient than internal combustion engines? Advantages and disadvantages. Let's go through those. The equations, just hopefully they're the same as what we just wrote down, which I think they are. The direct conversion of chemical energy to electrical energy without combustion, and that produces the heat loss. So if you did a Sankey diagram like you did back in year 8 physics or IB physics, you'd realise that there's much less energy wasted as heat. And then an advantage, no CO2 emissions locally, as long as the hydrogen is produced renewably and say by electrolysis from green electricity, wind power for example. But typically, in reality, hydrogen is produced from fossil fuel, steam reforming for example, and much of the rest of the questions are basically the same one here, but I'll just put them up so you can look at them. So challenge associated with using methanol, it's its toxicity. Also, you do get carbon dioxide emissions, but methanol might be produced in such a way that it takes in carbon dioxide when being produced. And again, methanol having a high energy density is an important idea. Avoid the issues of storing high pressurized gas. And there's a few thoughts there about evaluating the suitability of hydrogen and methanol for large-scale transportation. Let's have a look at those ideas there.